this off then, before the break, we found the value for the fourth constant, A, B, C, D, as a sixth. Okay? And if you carry on, you could find out what all the others are. But a pattern, hopefully, will start to emerge. And if you think back to the first slide again, where we had this power series for the exponential function, it had this factorial in it. Now, if we look at what we've been doing, and I've written them out, actually, while you're at the break, we can maybe see the pattern. Look. We take this function, here it is, the general function, a plus bx plus cx squared, and so on. And what we've been trying to do is find the values of a and b and c. And we differentiate it, and that means the a disappears, so we're just left with this. And then we differentiated it again, so the b disappeared and left us with this. But what I've done when I did the differentiation is, instead of writing this as a 6, which is this one, if I differentiate this, I get 3 times 2 is 6 dx. Leave it as 3 times 2. And then when we differentiate it again, we're just going to be left with 3 times 2 times d. But look at this. If I differentiate this once, I get 4e to the x cubed. Differentiate it again, I get 4 times 3 ex squared. Differentiate it again, I get 4 times 3 times 2. And you start to see this 4 times 3 times 2 occurring. And if I were to carry on and look at some of these other terms up here, I'd see the same thing happening. 5, the x to the 5 term would be, first time I differentiate, it would be 5 times f. Then it would be 5 times 4, 5 times 4 times 3, and so on. So that's where the factorial comes from in it. Because the definition of factorial is this successive multiplication. Now, if we look at the values that we've got, look, b turned out to be 1. C turns out to be a half, which is 1 over whatever number we have in front of the C here. D turns out to be 1 over 3 times 2, which is 6. So what do you guess E will turn out to be? Which is 24, right. So, and so on. So in other words, what are the values of the coefficients that go next to these things? It's 1 over the factorial. That's okay, that's where the factorial comes from. So now if we go back to the original, then we can actually write down the general term. So therefore, generally, e to the x, which is our function we're thinking about, can be written as a, which is 1, plus b lots of x, which is just x, plus x squared times a half, or 1 over 2 factorial, because 2 times 1 is just 2 anyway. So to keep the pattern going, we could write that as 2 factorial. Plus, we've got the x cubed now. What's the value of the coefficient that goes in front of the x cubed? This, which is 1 over 3 times 2, or just over 3 times 2. So this is over 3 factorial, and so on. Once we start to see the pattern emerging, we can then say, okay, I don't need to carry on applying the Maclaurin series anymore. I can just carry on and just write it. So the next term will be x to the 5 over 5 factorial, and so on. And we've come up with a power series for the exponential function. So what we do is we take our function and we find the value of the function when x equals 0. And that tells us the first constant. It tells us a. To get the second constant b, we need to differentiate it and then let that equal 0. The third constant, we differentiate it again and then let that equal 0, and so on. And that's the way we apply Maclaurin series. And we can write down what Maclaurin series is. And it says that any function can be written as the value of the function at 0 plus the value of the function, or the first differential of the function at 0, times x, because that's the x term. The next term, the x squared term, is going to be the second differential times x squared. The third term is going to be the value of the third differential at 0 times x cubed, and so on. And the nth term will be the nth differential at 0 times x to the n. So that's the general term. So that's all we've got to do. We've got to find out what the first differential is at 0, the second differential is at 0, and so on. And that is Maclaurin series. So all we're going to do now is going to set you off, and you can try and find Maclaurin's power series for quite a straightforward function, the sine function. So let's have a look at that. Use Maclaurin series to write sine x as a power series. And I'll just pause while you write this little table out and I'll explain. Okay, let's look at this thing then. So if I want to use Maclaurin series to write sine x as a power series, and in your assignment you're going to be doing something like this, okay? This is as good a way as any of setting it out. We've identified already that we're going to need to differentiate once, twice, 3 times, and so on. So what I do is I set out a little table. What's the function that I'm associating here? It's the sine function. So fx is sine x, because I'm finding the power function for the sine function, the power series for the sine function. F prime x, I write in here what the first differential of the sine is. What's the differential of sine? Cos. Now, to get the second differential, I differentiate this. What's the differential of cos? Or no, not sine to minus 1, minus sine. Cos it becomes minus sine, yep. Sine to the minus 1 means something else, doesn't it? Inverse sine, yep. Differentiate minus sine, I get minus cos. Differentiate minus cos. And then it starts to repeat, look, okay? When we do Maclaurin series, we're looking for patterns, which means we can then write down the series, because at some point we want to stop working out the differentials all the time and be able to just see the pattern, and often there is the case that there's a pattern. And then, when I've got my differentials, I then work out what the value of the function is at 0. So what's sine 0? Without doing it on a calculator, what's the sine of 0? Picture a sine wave. Right, a sine wave starts at 0, doesn't it? We're also going to need to be able to picture a cosine wave. A sine wave does this, doesn't it? A cosine wave does this. Starts at 1 minus 1. 1 minus 1. So, if we got those in our mind, we can almost write down what these differentials are. So what's the value of the function at 0? And what's the value of the first differential at 0? And so on. Okay? So then we say to ourselves, okay, let's write down this series. That's now told me what the first differential is. Yeah? So, sorry, the value of the function is 0 is, what the first differential is, what the second differential is, what the third differential is. And then I go back to Maclaurin series and plug them in here. So now I can write that sine x equals f0 plus the first differential at 0 times lots of x, plus the second differential at 0 lots of x squared, and so on. So in other words, this table allows me to find out the values of the coefficients. So see if you can write down work out what the power series for the sine function is.